There is something quietly extraordinary about the night sky. You have probably looked up at it before, maybe from a backyard, maybe from the window of a car on a long drive, maybe from somewhere far from the city where the stars seemed almost too many to count. And in those moments, it is easy to feel like you are seeing everything, like the universe in all its vastness is simply out there, open and available to anyone willing to look. But here is something worth sitting with tonight, something that scientists have been wrestling with for decades now, something that changes the way you understand every single thing you have ever seen or touched or felt. Almost everything that exists is invisible, not hidden behind a cloud, not waiting to be discovered with a better telescope. Invisible in a way that is so complete, so total, that no light in the universe, no radio wave, no X-ray, no beam of any kind can reveal it directly. You are lying in the dark right now, and the darkness around you feels empty. But darkness, as it turns out, is not empty at all. The space between things, the silence between stars, the void between galaxies, is filled with something. Multiple somethings, actually. Scientists have given them careful, honest names: dark matter and dark energy. The word dark here does not mean evil or frightening. It simply means unknown. It means we cannot see it. It means that our best instruments, the ones we spent billions of dollars building and launching into orbit, the ones sensitive enough to detect the faint glow of galaxies billions of light years away, even those cannot touch it directly. And yet, we know it is there. We know it the way you know the wind is blowing, even when you are inside with the curtains closed. If you enjoy these kinds of slow, deep journeys into the universe, the ones that make you feel small in the best possible way, then this channel might be exactly what you are looking for. Taking a moment to like this video and subscribe means you will find more of these waiting for you whenever you need them. It costs nothing, and it helps more than you might imagine. But for now, just settle in. Let your shoulders relax. Let your breathing slow down just a little. Because what we are about to explore together tonight is one of the most profound mysteries in all of science, and there is nowhere you need to be, and nothing you need to do except listen. So let us start at the beginning. Not the very beginning of the universe, we will get there gradually, but the beginning of the mystery. It starts with a woman named Vera Rubin, working quietly in the 1970s, doing the kind of slow, careful science that does not make headlines right away. Vera was studying galaxies, the way they spin, the way stars at the edges of a galaxy orbit the center compared to stars closer in. And what she found was wrong. Not wrong in a small, correctable way. Wrong in a way that meant something enormous was missing from our understanding of reality. She found that the outer stars of galaxies were moving too fast, much too fast. According to everything we knew about gravity and mass, those outer stars should be drifting slowly, lazily, like the outer planets of our solar system. Planets like Neptune and Uranus, which take centuries to complete a single orbit because they are so far from the sun's gravitational pull. But the stars at the edges of galaxies were not drifting, they were racing, and the only explanation that made any sense, the only one that preserved everything we knew about how gravity works, was that there was more mass out there than we could see. A lot more mass. Mass that did not glow, did not shine, did not emit or absorb any kind of light. Mass that was simply there, invisible and enormous. Think about that for a moment. Imagine you are watching a carousel at a fair. The horses on the outside should be moving faster than the ones in the middle, because they have more distance to cover in the same amount of time. But what Vera Rubin found was more like watching a merry-go-round where all the horses, inner and outer, are moving at exactly the same speed, regardless of where they are. And the only way to explain that is if there is extra weight hidden somewhere in the structure. Weight you cannot see. Weight that is changing how the whole machine behaves. That invisible weight is what we call dark matter. And it is not a small addition to the universe. It is. Not a footnote or a rounding error. According to the most careful measurements scientists have ever made, dark matter makes up roughly 27% of everything in the universe. The ordinary matter, the stars, the planets, the oceans, your body, everything you have ever touched or seen, makes up only about 5%. 5%. The rest is dark, and if that is not enough to sit quietly with for a moment, consider this. Even dark matter, as mysterious as it is not the strangest part, because there is something else out there. Something that does not just sit invisibly in space but actively pushes against the universe itself. Something that is causing galaxies to race away from each other faster and faster with every passing moment, as if the universe is being pulled apart from the inside by a force with no name we truly understand. We call it dark energy, and it makes up the remaining 68% of everything, which means that when you add up all, the dark matter and all the dark energy together, you get 95% of the universe, completely invisible, completely beyond the reach of any instrument we have ever built, and yet completely real, shaping every galaxy, every cluster of stars, every corner of the cosmos you will never visit. You are floating in it right now. You always have been. There is something almost meditative about that idea if you let yourself sit with it long enough. The universe you can see, the one with stars and moons and sunsets and the warm light of a lamp in a quiet room. That universe is a thin film, a visible crust over something unimaginably vast and dark and strange. And here is the thing about that darkness. It is not threatening. It is not waiting to harm you. It is simply there, doing what it does, keeping galaxies together, pushing the universe outward, going about its business with perfect indifference. It does not know you exist, and somehow that is comforting. When scientists first started encountering the evidence for dark matter, the natural reaction, the very human reaction, was to look for a mistake. Maybe the measurements were off. Maybe gravity did not work the same way at galactic scales as it did here, close to home. Maybe there was some other explanation. And so for years, some researchers proposed alternatives. One of the most famous was called MOND, Modified Newtonian Dynamics, which suggested that perhaps gravity behaves differently at very low accelerations, the kind you find at the edges of galaxies. It was a clever idea. It tried to explain Vera Rubin's rotating galaxies without invoking invisible mass. And for a while, it worked reasonably well for certain observations. But as more evidence came in, from gravitational lensing, from the cosmic microwave background, from the way galaxy clusters collide, MOND struggled to keep up. The evidence kept pointing back to the same conclusion. There is something there. Something massive. Something real. Something we simply cannot see. Gravitational lensing is one of the most beautiful confirmations of this. It is based on an idea from Einstein. The idea that mass bends space itself, and that light follows the curves of space the way a marble follows the curves of a bowl. So when light from a distant galaxy passes near a massive object on its way to us, that light gets bent, warped, curved. And if you know how much light should bend based on the visible mass of the object, you can calculate whether there is extra mass hiding there. And every single time scientists have done this calculation, every time they have looked at galaxy clusters and measured how much they are bending the light around them, they find more mass than they can see. The invisible mass is real. The gravitational fingerprints are everywhere. There is a particular galaxy cluster called the Bullet Cluster that has become something like a landmark in this story. It is the result of two galaxy clusters colliding, a cosmic event so slow and vast that it has been unfolding for millions of years and will continue unfolding for millions more. When these two clusters pass through each other, the ordinary matter, the gas and dust and visible material, slowed down. It collided, heated up, and got stuck in the middle, the way two clouds of smoke might merge and linger when they run into each other. But the dark matter did not slow down. It passed right through, indifferent to the collision, barely interacting with anything. And scientists could see this, not by observing the dark matter directly, but by mapping its gravitational effects. The dark matter kept moving forward while the ordinary matter fell behind. Two separate things, behaving in two completely different ways, leaving two completely separate gravitational footprints. It was, in a sense, the clearest picture anyone had ever taken of dark matter acting independently, and it was breathtaking. Consider, for a moment, what it means to discover something by its absence. You cannot see the dark matter in the bullet cluster. You cannot photograph it, measure it with a detector, or point to it and say, "There it is." What you can do is watch what happens around it. You can watch light bend where nothing visible exists. You can watch galaxies move in patterns that only make sense if something invisible is pulling them. You can watch the universe behave in ways that cannot be explained without it. This is science working the way it rarely gets to in popular stories, not with sudden discoveries and dramatic revelations, but with patient accumulation, with quiet certainty building slowly over decades, with evidence arriving from a dozen different directions and all of it pointing the same way. Dark matter is real. We just do not know what it is. And that is exactly where we are right now, on this particular night, in this particular moment in human history. We know it is there. We know roughly how much of it there is. We know how it clusters, how it influences the structure of the universe, how it helped gravity pull the first hydrogen atoms together into the first stars billions of years ago. Without dark matter, there might be no galaxies. Without galaxies, there are no stars. Without stars, there are no planets. Without planets, there is nothing and no one to wonder about any of this. In a very real sense, dark matter is why you exist, and yet we cannot name it, cannot catch it, cannot hold it still long enough to look at it properly. We know what it does without knowing what it is. There is something quietly humbling about that. Something that invites you to hold your certainty a little more loosely, to stay comfortable with not knowing, to find peace in the fact that the universe is larger and stranger than anything you can hold in your mind all at once. You are lying in the dark, and the dark is full of things you will never see and may never fully understand. That is not a frightening thought. It is an invitation to rest, to wonder, to let the mystery be as vast as it wants to be. And as you settle deeper into wherever you are right now, as your thoughts begin to slow and soften at the edges, the story of dark matter is only beginning to unfold. Because we have only covered one of the two great invisible forces in the universe. We have talked about what holds things together, the dark matter that wraps around galaxies like an invisible scaffold, keeping stars from flying apart into the void. But we have not yet talked about what is pulling everything apart. We have not yet talked about the force that is stretching the universe itself, accelerating its expansion, pushing galaxies away from each other faster with every passing second. A force so strange and so powerful that even the scientists who discovered it were not sure they believed their own data. That story begins with a group of astronomers in the 1990s who were trying to measure, with great precision, how fast the universe was growing, and who found, to their complete astonishment, that the answer was nothing like anything they had expected. The year was 1998, and two teams of astronomers were racing to answer one of the most important questions in cosmology. They were not racing against each other in a hostile way. Science rarely works like that, despite what the movies suggest. They were racing against the universe itself, trying to gather enough data, enough observations, enough careful measurements to finally pin down a number that had been elusive for decades. The question was simple to state and extraordinarily difficult to answer. Is the expansion of the universe slowing down, or is it not? Because after the Big Bang, everything flew outward, and gravity, the great gatherer, should have been pulling it all back together, gradually, patiently, the way a thrown ball eventually arcs back toward the Earth. The expansion should have been decelerating. Both teams fully expected to confirm that. They were not looking for a surprise. They were looking for a measurement. The tool they used was a specific type of exploding star called a Type Ia supernova. These explosions are remarkable for one particular reason. They are almost perfectly consistent. When a certain kind of dead star, a white dwarf, accumulates enough mass from a companion star and reaches a precise threshold, it explodes. And because the trigger, that threshold of mass, is always the same, the explosion is always roughly the same brightness. This makes them what astronomers call standard candles. If you know how bright something actually is, and you measure how bright it appears from where you are standing, you can calculate exactly how far away it is. The dimmer it looks, the farther away it must be. And by measuring how far away these supernovae were, and comparing that to how fast their host galaxies were moving away from us, both teams expected to find the deceleration they were looking for. They expected to see gravity winning. What they found instead was so unexpected that both teams spent months checking their data. They checked their instruments. They checked their calculations. They looked for systematic errors, for contamination, for any mundane explanation that might explain away what they were seeing, because what they were seeing was impossible, or at least it felt that way. The distant supernovae were dimmer than they should have been. Not slightly dimmer, measurably, consistently, unmistakably dimmer, which meant they were farther away than the models predicted, which meant the universe was not decelerating. The universe was accelerating. The galaxies were not slowing down as gravity pulled at them. They were speeding up. Something was pushing them apart. Something was winning against gravity, not just holding its own, but actively overpowering it on the largest scales imaginable. And nobody had any idea what that something was. They called it dark energy. It was not a triumphant naming. It was an honest admission of ignorance dressed in confident-sounding language. Dark energy is not a thing that was discovered and then named. Dark energy is a name given to a gap, a placeholder for a force or a property or a phenomenon that we know must exist because of what we observe, but that we cannot explain, cannot directly detect, and cannot even properly describe. It is the mathematical shape of something unknown, and it is, by the best measurements we have, the dominant component of the universe. Roughly 68% of everything that exists is dark energy, which means that when cosmologists build their models of the cosmos, the vast majority of what they are working with is a term in an equation that stands for, "We do not know what this is." Think about what that means in a quiet, unhurried way. Imagine you are reading a book and someone tells you that 68% of the words on every page are in a language no one has ever translated. You can see the effect those words have on the story. You can tell the plot is moving in a certain direction. You can feel the emotional weight of certain passages, but you cannot read them directly. You are inferring everything. You are working from context and consequence, from the shadows the words cast rather than the words themselves. That is roughly the position cosmologists are in. They can see the effect of dark energy in the acceleration of the universe. They can measure it, model it, include it in their equations, but the underlying nature of it, what it actually is, where it comes from, why it has the strength it has, remains completely open. One of the most elegant and strange things about dark energy is that it appears to be a property of space itself, not of matter, not of energy in the conventional sense, but of the vacuum, of emptiness. In quantum mechanics, which is the physics of the very small, empty space is not really empty. It is full of what physicists call quantum fluctuations, tiny temporary pairs of particles that pop into existence and annihilate each other almost instantly, like bubbles forming and collapsing in boiling water, except at scales so small and so fast that no instrument can directly observe them. This quantum frothing of the vacuum has energy, and some physicists believe that this vacuum energy is what dark energy is, that the universe is accelerating because empty space itself has a kind of outward pressure, a gentle but relentless push that never weakens, that does not dilute as the universe grows, and that over billions of years adds up to an irresistible force. But here is where things become genuinely strange, even by the standards of a conversation that already includes invisible mass and accelerating universes. When physicists calculate how much energy the quantum vacuum should have, when they do the calculation from first principles, using quantum mechanics and the best understanding of particle physics we have, the answer they get is so wildly, catastrophically wrong that it is almost funny. The predicted value of vacuum energy is approximately 10 to the power of 120 times larger than the observed value of dark energy. That is a 1 followed by 120 zeros. It is the largest discrepancy between theory and observation in the history of science. Not by a little, not by an order of magnitude, by a number so large it does not have a name in common language. Scientists sometimes call it the worst prediction in physics. And yet the observation is extremely precise. The dark energy is real, it is measurable, and it is exactly the right size to produce the acceleration we see. The theory is just spectacularly, bafflingly wrong about what that size should be. Have you ever had the experience of knowing something is true without being able to explain why? Not a hunch, but something deeper, a certainty that arrives without a full set of reasons, a conclusion that feels solid even when the path to it is unclear. That is a little bit like the position dark energy puts cosmologists in. They know it is real. The evidence is overwhelming. But the theoretical framework that should explain it is not just incomplete. It is producing answers that are off by the largest factor ever recorded in scientific history. Something is deeply wrong with the way we are thinking about it, and no one yet knows what. There is a name for the leading mathematical description of dark energy. It is called the cosmological constant, and it has a history that is almost as strange as dark energy itself. Einstein introduced it in 1917 when he was working out the implications of his general theory of relativity for the universe as a whole. At the time, the prevailing belief was that the universe was static, neither expanding nor contracting. But Einstein's equations kept producing a dynamic universe, one that wanted to move. So he added a term to his equations, the cosmological constant, represented by the Greek letter lambda, that acted as a kind of counterpressure, balancing gravity and keeping the universe still. He later called it his greatest blunder, after Edwin Hubble showed in the 1920s that the universe was actually expanding all along. Einstein removed the constant and moved on. But the universe, it turns out, was not done with it. When dark energy was discovered in 1998, physicists went back to Einstein's equations and found that the cosmological constant fit perfectly. Not because they forced it to fit, but because it was already there. A mathematical shape that described exactly the kind of constant, space-filling energy the observations were demanding. Einstein's blunder became the best description of the universe's dominant force. Consider for a moment the quiet irony of that. A correction Einstein introduced to preserve a universe he believed in, and then discarded when that belief turned out to be wrong. Turned out to be the best mathematical tool available for describing something no one knew existed when he was alive. Science does not move in straight lines. It curves and doubles back and occasionally discovers that the roads it abandoned were the right ones after all. The universe is under no obligation to be simple or to follow the paths we expect. Now, let us bring dark matter and dark energy back into the same frame for a moment, because they are two very different kinds of unknown, and it is worth feeling the difference between them. Dark matter is invisible, but it behaves in familiar ways. It has mass. It gravitates. It clusters around galaxies. It helped build the large-scale structure of the universe, the great filaments and sheets and voids that make the cosmos look, on the largest scales, like a vast three-dimensional web. Dark matter is strange because we cannot see it, but once you accept that it exists, it plays by the rules. It fits into the story of gravity and mass and structure formation in a way that makes sense, even if we do not know what the matter itself is made of. Dark energy is different in a more fundamental way. It does not cluster. It does not gather. It is perfectly smooth and uniform throughout the universe, present in equal amounts everywhere, in the space between galaxies and in the space between atoms. And rather than attracting things together, it repels. It pushes. It drives the universe apart with a force that grows as the universe grows. Because as space expands, there is more space, and more space means more dark energy, and more dark energy means faster expansion. and faster expansion means even more space, and on forever, in a process that has no natural end. Think of it like this. Imagine you have a jar of honey, and you're trying to carry it across a room. Gravity is the weight of the jar, constant, present, always pulling you toward the floor. Dark matter is extra hidden weight you did not know was in the jar, making it harder to carry. Dark energy is something different altogether. It is as if the floor itself is tilting away from you, gently but persistently, so that no matter how hard you walk, the other side of the room keeps moving slightly farther away, and the faster you walk, the faster it tilts. The destination does not recede because you are slow. It recedes because the space between you and it is growing, silently and ceaselessly, at a rate that nothing you do can change. This is actually happening right now to every galaxy in the universe beyond a certain distance from us. There is a boundary, not a physical wall, but a distance threshold, beyond which the space between those galaxies and ours is expanding faster than light can travel across it. Not because anything is moving faster than light. Space itself is stretching, and stretching is not the same as moving. The rule that nothing can travel faster than light applies to things moving through space, not to the expansion of space itself. So the galaxies beyond that boundary are not racing away from us. They are simply being carried away by the stretching of the space between us, and they are being carried faster than light can follow. They are, in a very real and permanent sense, beyond our reach forever. No signal we send will ever reach them. No light from them will ever reach us again. They are already gone, even though they will continue to exist. And every year, as the expansion continues to accelerate, a few more galaxies cross that boundary. The observable universe, the part we can ever know anything about, is slowly shrinking, not because the galaxies within it are disappearing, but because the ones at the edges are being carried beyond contact. There is something almost melancholy about that, if you let yourself feel it for a moment. The universe is vast beyond all reckoning. Hundreds of billions of galaxies, each containing hundreds of billions of stars, each star potentially orbited by worlds we will never visit and cannot imagine. And even that almost incomprehensible vastness is just the part we can see, the part we can know. Beyond it, receding forever, is everything else. An infinite dark sea of galaxies sailing away in silence, unreachable, unknowable, beautiful in their inaccessibility. You will never see them. No one will. And that is all right. There is enough wonder in the reachable universe to fill 1,000 lifetimes of quiet, sleepy contemplation. What does it mean for the future, this relentless acceleration? Scientists who study the long-term fate of the universe have mapped out several possible endings, and they depend almost entirely on the nature of dark energy, which, as we have established, is something we do not fully understand. If dark energy remains constant, if it continues at exactly the strength we observe today, neither growing nor weakening, then the universe will continue expanding forever. But everything within each gravitationally bound region will stay together. Our galaxy, the Milky Way, will eventually merge with the Andromeda Galaxy, and the resulting structure will persist for trillions of years, long after the last stars have burned out, a dark and cold and quiet remnant of everything that once blazed and burned. That is one possibility, a long, cold, quiet end. But if dark energy is not constant, if its strength grows over time, then the future becomes far stranger. Some models suggest that dark energy could intensify without limit, eventually becoming so strong that it overcomes not just the gravity between galaxies, but the gravity between stars, and then the forces holding planets together, and then the forces holding molecules together, and then eventually the forces holding atoms together. In this scenario, called the Big Rip, the universe does not simply expand into a cold, dark stillness. It tears apart. Galaxies are shredded. Stars are pulled into isolated atoms. Every structure that gravity or electromagnetism ever assembled, every rock, every ocean, every living thing, every atom, comes undone. not with drama or noise, but with the quiet, relentless overpowering of every bond that holds matter together. The universe returns, in a sense, to the smoothest and most uniform state imaginable. A perfect, cold, expanding nothing. That sounds frightening when you say it quickly, but try to hold it from a distance, the way you would hold a very old map, with curiosity and a kind of affectionate awe for how much is still unknown. The Big Rip, if it happens, would not occur for trillions of years. Not billions, trillions. The entire current age of the universe is only about 13.8 billion years. A trillion is 1,000 billion. The timescales involved are so far beyond anything human language was built to handle that they belong to a different category of existence entirely. You are here now, in a particular moment, in a particular galaxy, on a particular planet, in a warm and comfortable room, drifting towards sleep. The trillion-year future of the universe is as remote from this moment as the quantum vibrations of a single electron are from the orbit of a planet. It is real, but it is somewhere else entirely, and yet knowing about it changes something. Knowing that the universe is not static, not permanent, not simply there and always will be, that it has a history and a trajectory and a possible end, adds a kind of depth to the ordinary moments. The light from a lamp, the warmth under a blanket, the sound of your own breathing slowing in the dark. These are not small things. They are the outputs of a universe that has been organizing itself for almost 14 billion years, pulling hydrogen out of the void, fusing it into heavier elements in the hearts of stars, scattering those elements in great explosions across the galaxy, letting gravity and chemistry and time assemble them into something complicated enough to lie in a room and wonder where it all came from. You are the universe looking at itself. That is not a metaphor. It is a description of what is actually happening. The dark matter is out there right now, woven through the galaxy in a vast invisible web, shepherding stars that will never know it exists. The dark energy is out there, in every cubic centimeter of space, in the gaps between atoms and the voids between galaxy clusters, pressing outward with a patience and a persistence that no human institution will ever match. And you are here, somewhere in the middle of all of it, made of the visible 5%, the thin, bright film on the surface of an invisible ocean, wondering about the water. There is something in that image worth returning to as you settle deeper into the quiet. The mystery is real. The questions are real. And the not knowing is not a failure of science. It is science working exactly as it should, honestly naming its limits, honestly marking what it cannot yet see. The universe does not owe us explanations. It does not owe us transparency or simplicity or a clear view of what it is made of. It offers what it offers. Light bending around invisible mass, galaxies racing apart from each other, ancient starlight carrying messages from the distant past, and it asks us to be patient and curious and humble enough to follow where the evidence leads, even when it leads somewhere strange. And it does lead somewhere strange. It always has. From the moment Vera Rubin stared at her data and understood that the galaxies were not behaving the way they should, to the moment two teams of astronomers looked at dimmer-than-expected supernovae and understood that the universe was not decelerating the way it should, the story of dark matter and dark energy has been a story of the universe quietly insisting on its own complexity, its own depth, its own refusal to be fully known. And that story is not finished. It is not even close to finished. There are experiments running right now, underground detectors and space telescopes and particle accelerators, all of them reaching for that invisible 95%, all of them listening for a signal that has not yet come. What they are listening for, and why it matters more than almost anything in science today, is where the story turns next, and that is exactly where we are headed. Part 3. There is a particular kind of patience that science requires, and it is not the patience of waiting for something you expect. It is the patience of waiting for something you cannot predict, in a direction you cannot fully anticipate, using instruments built to detect things that might not exist in any form your instruments were designed to find. That is where the search for dark matter stands right now. not stuck, not failed, but suspended in a kind of alert and open stillness, the way you might stand at the edge of a very quiet forest at dusk, listening for a sound you have never heard before and would not be able to name if you heard it. The scientists running these experiments know something is out there. They have known it for decades. They are simply waiting for it to introduce itself. The most straightforward approach to finding dark matter has been to build a detector and wait for a dark matter particle to bump into it. This sounds simple in the way that all great ideas sound simple when you reduce them to a sentence. The actual execution is something else entirely. Because dark matter, whatever it is, interacts with ordinary matter so weakly that it passes through almost everything without leaving a trace. Through walls, through the earth, through you. Right now, if the leading models are correct, dark matter particles are passing through your body at a rate of millions per second, and not one of them is leaving any sign that it was ever there. You are a ghost to dark matter. Dark matter is a ghost to you. Two invisible things to each. Other, sharing the same space, completely unaware. To catch something that barely interacts with anything, you need to go somewhere very quiet. Not quiet in the acoustic sense, though that helps. Quiet in a deeper sense. Shielded from the constant rain of cosmic rays and natural radiation that would otherwise drown out any signal you were trying to measure. The best place to find that kind of quiet is deep underground. And so the most sensitive dark matter detectors in the world sit at the bottom of mines, beneath mountains, under kilometers of rock that block almost everything except, in theory, the dark matter that slides through stone as easily as light slides through glass. These are remarkable places. Cold, dim, extraordinarily still. The detectors themselves are marvels of engineering. Tanks filled with liquid xenon or germanium crystals kept at temperatures close to absolute zero, surrounded by layers of shielding, monitored by sensors sensitive enough to detect the faint flicker of a single particle interaction. And so far they have found nothing. Not failure, nothing, which is a different thing. Each null result is information. Each experiment that does not find a signal narrows the space of possibilities, rules out certain masses and interaction strengths, and forces theorists to revise their models. The absence of a signal is a kind of finding. It is the universe saying, quietly and patiently, not that way, try again. And so they do. Larger detectors, deeper locations, lower temperatures, better shielding. The search continues, and the constraints on dark matter grow tighter with every passing year, even as the particle itself remains stubbornly absent from every trap set for it. There is a candidate that has dominated the theoretical landscape for decades, and it goes by the somewhat ungainly name of WIMP, Weakly Interacting Massive Particle. A WIMP, as the name suggests, would be a particle with mass, real gravitational mass, enough to account for the dark matter we know is there, but with interaction so faint that it would pass through ordinary matter almost without noticing it. The appeal of WIMPs was never just that they fit the observational data, though they did. The appeal was deeper than that. They emerged naturally from certain extensions of particle physics theory, extensions that were being developed for entirely unrelated reasons, to solve problems that had nothing to do with dark matter. The fact that the math kept producing a particle that looked exactly like what the astronomers needed felt like more than a coincidence. It felt like a convergence, two different paths through two different landscapes arriving at the same unexpected destination. Physicists called it the WIMP miracle. But the WIMP miracle has been tested, and tested, and tested again, and the WIMPs have not shown up. The detectors have not found them. The particle accelerators have not produced them. The gamma-ray telescopes looking for the faint glow of WIMPs annihilating each other at the centers of galaxies have not seen the signal they would produce. This does not mean WIMPs do not exist. It means that if they do, they are hiding in a corner of parameter space that our current instruments cannot quite reach. Or it means that dark matter is something else entirely, something the theorists have not yet written down, something waiting to be imagined. The search is not over. It has barely begun in the long time scale of science. Consider for a moment what it means that we do not yet know. There was a time when humans did not know that atoms existed. There was a time when the germ theory of disease was not known, when the structure of DNA was not known, when the existence of other galaxies was not known. Each of those unknowns sat at the edge of human understanding for a while, inaccessible, impenetrable, and then something shifted. A new instrument, a new idea, a new way of asking the question. And what was hidden became visible. The history of science is largely a history of the invisible becoming seen. There is no particular reason to believe that history is finished. There is every reason to believe that dark matter is simply the next great transition, waiting for its moment, waiting for the right combination of imagination and technology to finally pull it into the light, or into whatever the equivalent of light is for something that does not interact with light at all. Axions are another candidate worth holding gently in your mind tonight. They are almost the opposite of WIMPs. Instead of being heavy, they are extraordinarily light. So light that the word light barely captures it. If WIMPs are boulders, axions are whispers. They were originally proposed not to explain dark matter but to solve a completely different problem in particle physics. A puzzle about why the strong nuclear force, the force that holds atomic nuclei together, behaves the way it does. And then someone noticed that the axion, this particle invented for one purpose, also had properties that made it a plausible dark matter candidate. Again, that sense of convergence. Again, different roads arriving at the same unexpected place. Experiments are running right now to look for axions, using powerful magnetic fields and extraordinarily sensitive detectors, and the results are not yet in. The axion has not shown itself. But the search is young, and the parameter space is large, and science is patient, in the way that only institutions spanning generations can afford to be. There are wilder ideas, too. Some physicists have proposed that dark matter might be made of primordial black holes that formed not from collapsing stars, but directly from density fluctuations in the very early universe, before any stars existed. These would not be the massive black holes at the centers of galaxies. They would be small, perhaps the mass of an asteroid or a planet, distributed throughout the cosmos like invisible dark seeds. They would not emit light. They would not interact with ordinary matter except through gravity. They would pass through the galaxy in enormous numbers, silent and slow and invisible. Measurements of gravitational lensing have constrained this idea significantly. If primordial black holes made up all the dark matter, they should occasionally pass in front of distant stars and briefly brighten them through lensing, and surveys looking for those brightenings have come up short. But primordial black holes have not been entirely ruled out. Some versions of the idea still survive in the narrowed space the data allows. What all of these candidates share is the property that makes dark matter so hard to study. They do not interact with light. And light is how we know almost everything we know. Every telescope ever built, from Galileo's first crude instrument to the James Webb Space Telescope, floating silently in its orbit 1,000,000 miles from Earth, works by collecting light. Every image of a nebula, every spectrum of a distant star, every photograph of a galaxy cluster, all of it is light. We have built our entire picture of the universe out of photons, out of the electromagnetic spectrum in all its forms, from radio waves to gamma rays. And dark matter is simply not there in that picture. It exists in a parallel layer, one that intersects with the visible universe through gravity and only through gravity, invisible to every photon-based instrument ever devised. To find it, we need to either catch it in a detector when it happens to interact with ordinary matter, in the extraordinarily rare and faint way theory suggests it might, or we need to find some entirely new approach, some window into the dark that we have not yet imagined. And here is what is quietly astonishing about that situation. We have known about dark matter for roughly 50 years. We have been actively searching for it with sophisticated instruments for more than 30, and we have not found it. In that same period, we have discovered gravitational waves, ripples in spacetime itself, predicted by Einstein a century ago, detected for the first time in 2015 by instruments so sensitive they could measure a change in distance 1,000th the width of a proton. We have imaged a black hole directly, something that seemed impossible not long ago. We have landed rovers on Mars, sent probes past every planet in the solar system, detected thousands of planets orbiting other stars, mapped the cosmic microwave background with extraordinary precision. Science has not been standing still. It has been moving with breathtaking speed and producing wonders at a rate that would have seemed like fantasy a few generations ago. And through all of it, dark matter has remained exactly where it was when Vera Rubin first noticed the galaxies were spinning wrong, present, certain, and completely out of reach. That persistence of mystery is worth sitting with, quietly and without frustration. Some things take longer than others. Some questions are harder than others. The universe has been dark for far longer than it has been studied, and it carries its secrets with the indifference of something that does not know it has them. There is a kind of beauty in that, in the idea that the cosmos is not performing for us, not arranging itself to be understood, not making things easy or hard based on any sense of what we deserve. It simply is, in all its invisible complexity, and we are here at the edge of it, asking. The asking is the remarkable thing, not the answering. Think about the dark energy for a moment more as you settle deeper into this quiet. We said it fills all of space. We said it is uniform, smooth, present in equal measure everywhere, and we said it is pushing the universe apart. But there is something more to sit with, something that connects dark energy to the most intimate and immediate experience of being alive. You are breathing right now, slowly, in and out. Each breath takes in air, mixes it with what your body needs, and releases what it does not. That process, that exchange, happens because of chemistry, and chemistry happens because of atoms, and atoms have the structures they have because of the forces that hold them together. The electromagnetic force, the nuclear forces, the fundamental rules of quantum mechanics. All of those forces, all of those rules, emerged from the same early universe that also produced dark energy. They are not separate. They are chapters in the same story. The force that is pulling distant galaxies apart is a sibling of the force that holds the molecules of your body together, in the sense that both emerged from the same origin. The same initial conditions, the same first few moments of a universe that was once impossibly small and hot and uniform. You are connected to dark energy not by any mystical thread but by physics, by the simple fact that everything that exists came from the same place and is governed by the same underlying rules, even the rules we have not yet written down. The darkness that fills the universe is your darkness too, in the most literal and scientific sense. The invisible scaffolding of dark matter that shaped the galaxy you were born into is as much a part of your history as the star that formed the atoms in your body. You did not choose any of it. Neither did the universe. It simply unfolded from that first incomprehensible moment through 14 billion years of cooling and collapsing and exploding and expanding, all the way to this. A particular arrangement of atoms on a particular planet, listening to a quiet voice describe the invisible ocean it is swimming in. Does that feel large to you? Does it feel like too much to hold? That is the right response. The appropriate response to the scale of the universe is not comfort and not dread, but something in between, a kind of reverent disorientation, the feeling of standing at the edge of something so vast that the edges of your own awareness soften and blur. Scientists feel this too, the ones who have spent their careers studying the dark. They describe moments of looking at the data, at the rotation curves of galaxies, at the maps of the cosmic web, at the equations that describe the expansion of space-time, and feeling beneath the mathematics something that does not have a scientific name, something like wonder, something like vertigo, something like the quiet recognition that the universe is not a problem to be solved, but a presence to be inhabited. And we inhabit it so briefly. The human lifespan, even a long and fortunate one, is an eye blink against the age of the universe, and the age of the universe is itself a relatively early chapter in the story the universe will eventually tell. The stars that exist today are young by cosmological standards. The universe is still in what some astronomers call its stelliferous era, the age of stars, when hydrogen is still abundant enough to fuel new suns, when galaxies are still bright enough to be seen across billions of light years. This era will last for trillions of years, but it will end. The hydrogen will run out. The stars will die. The last red dwarf will flicker and cool in some unimaginable future, and the universe will enter a long, dark age of cold, stellar remnants and slowly evaporating black holes, an epoch so long and so dark that the stelliferous era, our entire cosmic neighborhood, everything we have ever seen or known, will seem like a brief, bright spark at the beginning of a very long night. You are in that spark, right now, at this moment, in the bright and warm and living part of the universe's history, surrounded by stars, on a planet that still has oceans and atmosphere and the particular combination of chemistry and warmth that allows things like thought and sleep and wonder. That is not something to take lightly, not something to rush past. It is something to lie quietly with, here in the dark, on this particular night, letting the weight of it settle gently over you like something warm and familiar. The dark matter is out there right now, woven through this galaxy in filaments you will never see, holding the spiral arms of the Milky Way in their gentle, ancient shape. The dark energy is in this room, in the space between the atoms of the air you are breathing, in the space between the walls and the space between your cells, present and smooth and perfectly indifferent, pressing outward in every direction with the same quiet force it has been pressing with since the beginning. You are swimming in the invisible universe. You always have been, and it has always been carrying you, not toward anything in particular, not away from anything in particular, but simply outward, the way the universe has always been going, since the first moment of its existence, outward into the dark. There are things we will understand, given time. There are detectors being built right now that are larger and more sensitive than anything that came before them. There are theorists writing equations on whiteboards and screens in universities all over the world, trying out new ideas, combining old ones in new ways, following the mathematics wherever it leads. There is a generation of scientists who have grown up knowing about dark matter and dark energy the way earlier generations grew up knowing about atoms, as a given, as a fact of nature, as something real that simply awaits explanation. And someday, perhaps, one of them will find the right approach, the right instrument, the right question to ask, and the dark will become a little less dark. A particle will leave a signal in a detector deep underground. A telescope will catch a pattern in the sky that only makes sense if a certain kind of invisible matter is there. An equation will simplify in exactly the right way and reveal something previously hidden. It will happen. Maybe not soon. Maybe not in any lifetime currently being lived, but it will happen. Until then, the mystery remains. And the mystery is not a wound or a failure. It is an inheritance. It is the universe handing down, generation to generation, the most important questions it has, the ones that resist easy answers, the ones that require patience and imagination, and the willingness to sit for a very long time with something you cannot fully see or touch or name. Those questions are a gift. Not everyone gets to live in a time when the most fundamental questions about the nature of reality are still open, still alive, still waiting for the right mind to find the right way in. You live in that time. This is that moment. The invisible universe is all around you, and it is real, and it is vast, and it is, in its way, extraordinarily beautiful. Let your thoughts go where they want to go now. Let them drift out past the walls of wherever you are, past the atmosphere, past the moon, and the sun and the outer planets, out into the space between the stars where the dark matter gathers in slow, invisible clouds, out past the edge of the galaxy where the last stars thin out into the void, out into the intergalactic space where almost nothing exists except dark energy and the faint afterglow of ancient light. You can go as far as you want. There is no edge to run into, no wall to stop you. The universe in that direction is open forever, expanding gently in every direction at once, carrying everything that exists outward into a darkness that is not empty but full of things we cannot see, cannot name, cannot yet imagine. And in all of that vastness, in all of that invisible immensity, there is this: a small, warm planet, a quiet room, a person lying in the dark, breathing slowly, letting the thoughts come loose from their moorings and drift apart, one by one, like stars on the edge of a galaxy slowly drifting into the deep. You are here. The universe is here. The darkness between you and the farthest galaxy is the same darkness that is in this room right now, and it is gentle, and it is old, and it has been here long before there were eyes to see it or minds to wonder about it. It asks nothing of you. It expects nothing. It simply continues, as it always has, outward and onward, patient and vast and dark and full. Rest now. The invisible universe will still be there when you wake. It will be exactly where you left it, doing exactly what it has always done, holding galaxies together, pulling space apart, keeping its secrets with perfect, unhurried grace. The questions will be waiting too, unchanged, ready to be picked up again in the daylight. But for now, there is nothing to figure out, nothing to solve, nothing to reach for or hold on to. Just this breath, and the next one, and the quiet dark around you, full of things beyond counting, carrying you gently forward through the night. Good night.